Okay, for today, we'll pick up near the end of chapter 7, where we left off last time, particularly on page 384 or 394, depending on which version of the book you're using. Um, the book goes into a little bit of detail on multicenter molecules, which is something I don't really want to spend a lot of time on. Obviously, if you look at the notes, um, most of the molecules that we encounter here in general chemistry will be the type that we've seen so far, with one central atom and the other atoms bonded to it, arranged around it. But obviously not all molecules are like that. When it comes right down to it, most molecules are not like that. Most molecules have, chains of atoms, or they basically have a bunch of atoms bonded together, and there's no one single atom that qualifies as the central atom in the molecule. And that would be what's known as multicenter molecules. And what you would have to do with those is sort of focus on each central atom. That is, don't focus on the outermost atoms, but focus on the atoms that are, say, second from the outermost end of the molecule, and look at each of those individually. Total up the number of electron regions around those atoms, and decide on what the geometry of each of those atoms is individually. So when you have molecules, like a lot of organic molecules that have lots of single bonded carbons in them, well, you look at each carbon individually and you find out that each carbon is tetrahedral, because each carbon has 4 regions of electrons around it. And so each individual carbon, and if they're all single bonded, would be tetrahedral. And then you can build up the shape of the larger molecule based on that information. And that's even how, a lot of mapping of shapes of molecules today is done with software, but that's even how the software does it. It looks at each individual molecule, finds the shape around that molecule, and then sort of combines them all together into one overall shape. But I'm not going to ask you to do anything too ambitious in that area, because I wanted to move on to things like molecular polarity and dipole moment. Notice I made a point of emphasizing molecular polarity and dipole moment. So here's where we're talking about, or at least ultimately, we're going to be interested in finding out whether the molecule itself is polar or nonpolar. We know from past experience that finding out whether a bond is polar or nonpolar is pretty easy. If the bond involves 2 different elements, it's polar, at least a little bit. And the only way you're going to get a bond that's totally nonpolar is if the 2 atoms involved are of the same element, like the bond between the 2 chlorine atoms in Cl2, or the bond between 2 carbon atoms in a lot of organic compounds where you have carbon-carbon bonds. Those bonds would be polar because the 2 elements are the same and they have the same attraction for electrons. If the elements are different, they're going to have a different electronegativity, or in other words, a different attraction for electrons, and the element with the higher electronegativity will pull the electrons closer, and that end of the bond will be partially negative, and the other element will have electrons pulled away from it, and that end of the bond will be partially positive. This results in a bond dipole moment. Dipole moment is just another way of saying that the bond is polar. And the symbol for a dipole moment is the Greek letter mu, which we last saw when we were talking about the metric system back at the beginning of the semester, because the letter mu is also the abbreviation for the metric prefix micro. Okay, so if it's in combination with a measurement and a base unit like meters or something, then mu stands for 10 to the minus 6. But if it's measurement of the polarity of a bond, then mu stands for dipole moment. And the letter mu in Greek is the equivalent of m in English. So obviously they chose that to represent the word moment. And basically the bigger the number for the dipole moment, the more polar the bond is. A totally nonpolar bond would have a dipole moment, or mu, of 0. And like I said, the bigger the number is, the more polar the bond is. mathematically mu is equal to QR, where Q is the magnitude of the partial charges on the atoms involved in the bond. And we get that from the difference in electronegativities between the two atoms. And R is the distance between the charges. And so you can tell by looking at this that the dipole moment will be greater if the charges, or the difference in the dipole moment will be greater if the difference in electronegativities is greater. So again, the greater the difference in electronegativities, the greater the dipole moment and the more polar the bond is. And it also tends to increase with distance between the charges, up to a limit anyway. Dipole moment can be considered a vector, and a vector is just a quantity that has both magnitude and direction. It's something we talk quite a bit about in physics, but it really only comes up in chemistry in terms of dipole moment. It has magnitude because you can do this equation here for any given bond and come up with a number for dipole moment, and that number is the magnitude. Dipole moment also has a direction because of what I was saying up here. One end of the bond has an atom with greater electronegativity, which pulls the electrons toward that end of the bond. And the other end of the bond has an atom with less electronegativity that has electrons pulled away from it. And so the direction of dipole moment is considered to be the direction in which the electrons are being pulled. So it has direction and magnitude, and so it's actually a vector, as we would call it in physics. You can draw the dipole moment in a polar bond by using an arrow to point in the direction in which the electrons are being pulled. And we make a little plus sign at the opposite end of the arrow on the end of the bond that the electrons are being pulled away from. So in the bond between hydrogen and chlorine, chlorine has a much higher electronegativity than hydrogen does, and so chlorine will pull the electrons in its direction. So you draw the arrow pointing toward the chlorine, and you make the little positive sign down at the end of the bond by the hydrogen, because the hydrogen is basically having its electrons pulled away from it. I mentioned here that ideally the length of the arrow is proportional to the difference in electronegativity. So if you draw the arrow fairly long, like I did, that would represent a very polar bond. And if it's a bond that's not very polar, then you would draw a tiny little short arrow. I can't guarantee that I'm always going to do that in practice when I'm drawing stuff because of my extremely limited artistic abilities. But when you're looking at dipole moments in the book anyway, that's the way it'll be. The shorter the arrow, the less polar the bond is. The longer the arrow, the more polar the bond is. You can look also at the water molecule, which we've now determined has a tetrahedral electron geometry because there are 4 regions of electrons on the oxygen, and 2 of them are bonding regions and 2 of them are lone pairs. So for the molecular geometry, you would only name where the atoms are, and the shape of the atoms, or the arrangement of the atoms, is known as bent. So water would have a tetrahedral electron geometry and a bent molecular geometry. The dipole moments would go from the hydrogen toward the oxygen because, as I mentioned before, oxygen is the second most electronegative element in the entire periodic table, and hydrogen is the least electronegative of the nonmetals, and so that's a very polar bond right there, and there are 2 of them. Now what we're going to wonder about next is, what about the polarity of the molecules? Because the polarity of bonds and the polarity of molecules are 2 separate considerations. You could have a molecule with polar bonds, and yet the molecule could be nonpolar. Okay, so really whether the molecule is polar or not depends on a couple of things. First of all, are the bonds polar? And how are the bonds arranged? Because it is, as it turns out, it is possible to arrange polar bonds in a way that their polarities cancel each other out, and you end up with a nonpolar molecule. Okay, so polarity of bonds and the arrangement of the bonds go into deciding whether the molecule is polar. The way we find out, if you want a number out of it anyway, then what you would have to do is what's known as vector addition, and take the magnitudes and directions of the vectors for all of the dipole moments in all of the bonds in the molecule and do a vector addition with them and find the resultant. And if the resultant is 0, then that means the molecule is nonpolar because the polarities cancel each other out. And if the resultant has a number, then that would mean, I mean, a number other than 0, then that would mean that the molecule is polar. In practice, since we don't usually need numbers for that kind of thing, at least not in general chemistry, we can find out whether the molecule is polar or not basically by looking at the molecule and just sort of thinking about what's going to happen when the polarities of the different bonds interact with each other. Okay. Okay, so in a case like water, where you have the bent molecular geometry, the polarity of, basically the way I've drawn it here, you can draw it with the hydrogens on the bottom and the oxygen on top. So the way I've drawn it, the bond polarity is going to be from hydrogen to oxygen. So here we have oxygen pulling electrons sort of up diagonally to the right away from this hydrogen, and up diagonally to the left from this hydrogen, and left and right would tend to cancel each other out. But what both of those bond polarities have in common is they're both pulling upward. And so the resultant of these two vectors would be going upward in that direction. And the fact that there is a resultant, I mean, you know, the resultant's not 0, would tell you that this molecule must be polar. And you can see it right here. I mean, the hydrogens are both on the bottom, so that end of the molecule is going to be partially negative, and the oxygen is on top, so that part of the molecule is going to be partially positive. So it makes sense that that would be a polar molecule with polar bonds. On the other hand, something like carbon dioxide has polar bonds, but when you do the VSEPR theory on it, you find out that those polar bonds are directly across from one another, 180 degrees apart. So the oxygen is pulling electrons away from the carbon directly to the right, and the other oxygen is pulling electrons away from the carbon directly to the left with the same amount of force, if you want to think of it like that. And that means that the two dipole moments from the carbon-oxygen bonds cancel each other out. And so you end up with a molecule that has polar bonds, but the molecule is nonpolar. And the same happens with a tetrahedral molecule like carbon tetrachloride. The carbon has four regions of electrons around it, and each of those regions of electrons is a bonding pair of electrons between carbon and chlorine, and the chlorine is going to be pulling electrons away from the carbon in each of these bonds. And with the bonds being evenly spaced around the carbon in three dimensions, again, the bond polarities end up canceling each other out. So CCl4 is a molecule with polar bonds, but the molecule itself is nonpolar. On the other hand, if you have nonpolar bonds, you normally end up having a nonpolar molecule, like in the case of O2 or Cl2. The bond is nonpolar. The electrons are evenly attracted or evenly distributed between the two atoms at either end of the bonds. And so there's no positive end and there's no negative end for the bond. And since in this case, the bond is the entire molecule, there's no polarity for the molecule. So this would be nonpolar bonds, nonpolar molecules. The book doesn't really mention it, although it shows lots of examples, so you might be able to deduce it on your own if you really think about it. But there is a general rule of thumb that's almost always true, and that is that if all of the outer atoms are the same, and there are no lone pairs on the central atom, then the molecule is probably nonpolar, even if the bonds are polar. And we can look at the examples we did above. Okay, on the H2O molecule, the outer atoms are the same as each other, but there are two lone pairs on the outer atom. So this molecule ends up being polar. On the carbon dioxide, both outer atoms are the same, and there are no lone pairs on the central atom. So according to our rule of thumb here, that molecule is probably nonpolar, and it is. Same with CCl4. All of the outer atoms are the same, and there are no lone pairs on the central atom. And sure enough, it's nonpolar. And the other rule of thumb is, on the other hand, if the outer atoms are not all the same, or if there's one or more lone pairs on the central atom, then the molecule is probably polar. We saw the part about the lone pairs on the central atom with H2O. So that's polar. An example of something with different outer atoms might be CH3Cl, or methyl chloride. It has a tetrahedral shape, and let's see, 3 of the 4 outer atoms are the same, but the 4th one is different. And so these bonds are all polar to some extent. The carbon-hydrogen bond is not very polar, but it's a little bit polar. The carbon-chlorine bond is pretty polar. And so the result is carbon will be pulling in electrons from the hydrogens, but not very strongly. But the chlorine, will be pulling in electrons from the carbon very strongly. And so you've got a bond polarity that's pulling this way, and one that's pulling that way, and one that's pulling that way, and one that's pulling that way. So the resultant would be more or less pulling, it's more or less to the right anyway. So the fact that you've got one outer atom that's different messes everything up, and it throws the molecule off balance, if you want to think of it that way, and that means the molecule is polar. Okay, so that's these rules of thumb here are pretty useful in practice, and there are some exceptions to them, but not very many, and you don't encounter the exceptions very often. Some of the properties of polar versus nonpolar molecules would be that, for one thing, polar molecules will align in an electric field because there's a separation between the positive and negative charges in polar molecules. They will align with an electric field, which is a flow of electrons, so that makes sense. Nonpolar molecules will not align with an electric field. Polar molecules are attracted to each other fairly strongly. And that's because polar molecules have part of the molecule that's positive and part of the molecule that's negative, and those opposite charges will be attracted to each other. So you'll have the positive part of one molecule attracted to the negative part of the molecule next door, and vice versa. And so they're fairly strongly attracted to each other. Nonpolar molecules, on the other hand, tend not to be attracted to each other, except under maybe extreme circumstances. You can think of it like that, like really low temperature, or if the molecule is really, really big. But for polar molecules, they'll attract each other even if the molecule is small and even if the temperatures are high. Okay, so there's a difference. Also, when trying to dissolve something, we use the phrase like dissolves like, just meaning that polar molecules tend to dissolve in polar solvents like water, and nonpolar molecules tend to dissolve in nonpolar solvents like, say, benzene or gasoline or something like that. So something polar like, say, ammonia will dissolve very well in water, which is basically how they make Windex. Windex is mostly water, but the varieties that have ammonia in them, they dissolve ammonia in the water, and it dissolves quite readily in the water because it's polar. And on the other hand, if you try to dissolve something non-polar in water, like wax, candle wax is non-polar. Try to dissolve candle wax in water, it's not going to work very well. On the other hand, if you try to dissolve candle wax in something non-polar, like gasoline or benzene, it'll work very well because that's two non-polar substances. So essentially, like dissolves like. And that is the end of chapter 7. I didn't actually know that we were getting that close to the end of chapter 7, but here it is. So I will send out an email about the due date and the homework problems. I have to look at the calendar and see how much time we have left and that kind of thing. But so anyway, we're done with chapter 7, and I've still got a couple of minutes left in this segment of the lecture. So I'm going to take that opportunity to start in on chapter 8. There are parts of chapter 8 that are essentially a review for us, and so I'm not going to spend a lot of time on those parts of the chapter. I would like to, try and finish the chapter by the end of the semester. So we'll try to skip over the parts that are review, and it's things that you've already heard. Some of it, it's not just review, but some of it's stuff that you actually heard in the last chapter, in chapter 7. So it's not only review, but it's recent. Anyway, chapter 7 is on advanced theories of covalent bonding. I left out advanced because I didn't want to scare anybody off, but it's the theories of covalent bonding. So we're going to try to answer in this chapter questions like, how do covalent bonds form? Why do some bonds form and others don't? There are lots of bonds where lots of potential molecules where you can draw a very plausible Lewis structure for that molecule, and yet the molecule doesn't form because the bonds in the molecule won't form. And so a valid question would be, why not? The Lewis structure looks good. Why don't the bonds actually form? And this is where we'll find the answer in this chapter. Why do some molecules have shapes that shouldn't be possible by combining electrons in the types of orbitals that we've seen so far? S, P, D, and F orbitals have certain geometries, and if you're forming molecules by combining electrons that are in those types of orbitals, then molecules should be confined to a certain very small variety of shapes. But yet molecules are possible in a whole variety of other shapes that shouldn't be allowed by those types of orbitals. Why is that? Well, we're going to see in this chapter. And why do some molecules that seem similar exhibit different magnetic properties? So you put one molecule in a magnetic field and it's attracted to the magnet. You put another molecule in a magnetic field and it doesn't really care at all that there's a magnet there. And why is that? Well, we'll find out in this chapter. The first part of the chapter gets into valence bond theory, which is kind of the first step on our journey here. Sorry, excuse me. The VSEPR theory explains the shapes that molecules have, but it doesn't really explain why. In other words, how do the atoms bond together to give us those shapes? And particularly, what I said about the orbitals. There are a lot of molecular geometries that shouldn't be possible given the geometries of the S, P, D, and F orbitals. And so we want to know, how do bonds form? Why do some bonds form and not others? And of course, the question about the geometries. Quantum mechanics can give us the most likely locations for electrons around a nucleus of atoms, and those would be orbitals. But those are atomic orbitals, and they have a hard time explaining the shapes of molecules. And again, so that's the SPDF thing. The valence bond theory says that a covalent bond is an overlap of half-filled atomic orbitals, each with one electron, forming a pair of electrons. So you've got two orbitals on neighboring atoms. Each of them has one electron in it, and they come together and they overlap with each other, so that, say, the fingernail here is one electron and this fingernail is another electron. They come together and overlap so that now you've got a mutually formed orbital between the two atoms that has two electrons in it. And that's the valence bond theory of what a covalent bond is. There are a couple of things that have to happen in order for a covalent bond to occur. The orbitals of the two neighboring atoms have to overlap, and there has to be a single electron in each orbital so that they can form a pair when they overlap. If both of the orbitals are empty, nothing's going to happen. If one of them has one electron and the other has nothing, nothing's going to happen. If both of them have two electrons in them, nothing's going to happen. If one of them has a single electron and the other has two electrons, nothing's going to happen. It's only if there's one electron in each of them and they come together and overlap, only then can you get a bond. In practice, the attraction between the negative electron pair and the positive nucleus of the two atoms on either side of the electron pair that's being shared, that's what holds the bond together. The strength of the bond depends on the amount of overlap. In the valence bond theory, it's treated as a physical overlap of the two orbitals, and the more they overlap, it's like overlapping this much versus overlapping this much. The more they overlap, the stronger the bond is. Also, the distance between the atoms affects the strength. And we've seen before that chart with the optimum distance for two hydrogen atoms, where when the two hydrogen atoms are completely separate from each other, the energy is considered to be zero. And then as they approach each other, the energy starts declining below zero, negative energy. And when they reach a certain distance apart, the energy reaches a minimum. And if you try to push them any closer together, they start repelling each other and the energy goes back up again. So the point where they're at the minimum energy, that is the normal bond distance between two atoms involved in a covalent bond. So the optimum distance is the distance with the lowest energy. They've reproduced that figure as figure 8.2 on page 413 or 413 or 423, I guess. That would have to be. The exact distances depend on the elements involved. So hydrogen will be at like a shorter distance than something like, say, chlorine-chlorine bonds. Okay, the bond energy is just the difference between the minimum energy at the optimum distance and the zero energy when the atoms are separated by a large distance. It's usually considered to be an infinite distance, but of course in practice there's really no such thing as an infinite distance. Okay, so that the bond energy would be the energy released when the bond forms, and that same amount of energy is also the energy that you have to put in if you want to break the bond. And there is a table, once again, of bond energies and bond lengths. This table 8.1 on page 413, 423. And this is the same table we saw in the last chapter, but you can look at it and see the relationship between bond energies and bond lengths. You'll see that as bond energy goes up, the strength of the bond goes up, but the length of the bond goes down. So shorter bonds are stronger and longer bonds are weaker. Okay, before we start getting into the orbitals, I'm going to break here for segment A of the lecture because we're a little over time. So we'll come back and we'll talk about the orientation of orbitals that overlap to form bonds.